3IATLAS survived perihelion intact. Most comets don't. A cosmic documentary sleep story. Part 1, opening the question. Most comets don't stand a chance against the sun. They break apart, crumble, and vanish into dusty clouds, ancient ice boiling off in just minutes. But 3IATLAS, it survived. Welcome to a channel that digs into the weird and wonderful world of interstellar visitors. These are objects from other star systems, each one carrying mysteries we're only just starting to figure out. Tonight, we're diving into the story of something that shouldn't have made it but did. If you're curious about these cosmic oddballs, hit subscribe or drop a like. It takes a lot to put these videos together, and your support means a lot. Let's jump in. October 30th, 2025. The object called 3IATLAS swung in close to the Sun, reaching perihelion, just inside Mars's orbit about 1.4 astronomical units out. That's a rough neighborhood for any space rock. At that distance, the Sun's glare is fierce. Ice doesn't stand a chance, it vaporizes fast. Rock gets cooked. Anything flimsy falls apart. For months, telescopes everywhere, across the US and beyond, had their eyes on this thing, tracking its path and confirming it came from far outside our solar system. At 1.4 AU, the Sun blasts every square meter with about 360 watts. That's half of what we get on Earth, but it's still enough to roast anything exposed for long. Imagine 3 old-school light bulbs shining on every square meter of surface, non-stop for days. Only it's not just light. It's ultraviolet radiation that snaps molecules apart, and infrared that seeps deep into the comet, heating up layers of ice that haven't thawed since this object first formed, billions of years ago. Everyone expected the usual comet drama at perihelion. Fragments flying off, sudden outbursts, maybe a burst of brightness as sunlight hit fresh ice. Sometimes comets break up completely, the core splitting into dozens of drifting pieces. It's par for the course. When comets get too close to the Sun, thermal stress usually tears them apart. History is littered with comets that didn't make it. ISON, hyped up as the comet of the century in 2013, crumbled during its close pass, leaving just a faint cloud behind. Linear split up in 2000, the pieces fracturing again and again. Shoemaker-Levy 9 shattered into more than 20 chunks before slamming into Jupiter in 1994. Even another Atlas, different object, same name confusion, fell apart in 2020, letting down astronomers hopping for a show. The trend is clear. Comets are fragile, just loose lumps of ice and dust. No sturdy metal, no heavy gravity holding them together. When the side facing the Sun heats up quickly but the inside stays icy cold, the stress cracks the core. Gas from melting ice gets trapped, then bursts out wherever it finds a weak spot. If the comet's spinning, that adds another way for it to fly apart. Closer to the Sun, all those forces ramp up. But 3IATLAS, it broke the pattern. It came through perihelion in one piece. No big chunks flying off. No dramatic outbursts. None of the usual signs of a comet falling apart under pressure. And that's what's got astronomers uneasy, not so much what happened, but what didn't. It's not just a question of how it survived, but why an interstellar visitor could shrug off conditions that destroy comets from our own solar system all the time. This unease isn't all over the news. You won't find it in splashy headlines. It slips into the careful language scientists use in papers. Anomalously coherent structure, unexpected thermal resilience, survival contrary to standard fragmentation models. That's what researchers say when the numbers don't add up, but they're not ready to throw out the old theories. Not yet anyway. Sure, there are plenty of possible explanations. Maybe it's made mostly of rock. Maybe it's got a weird internal structure or a thick crust that kept the inside cool. All of those ideas are possible, nothing that breaks the laws of physics. But the more data comes in, the more the puzzle pieces just don't quite fit. The details keep nudging at the boundaries of what we've seen before. Take what we know about comet cores. Usually they're porous, full of holes and weak spots. Spacecraft measurements show they're often less dense than water ice, meaning there's a lot of empty space inside. For example, Rosetta's close look at Comet 67P found it had a density of just 533 kilograms per cubic meter, about half that of water ice, much less than solid rock. That kind of fluffiness makes comets easy to break. Weak structure, lots of ways for gas to leak out, plenty of failure points when things heat up. If 3IATLAS is as porous as we think, it should have broken apart. But if it's tougher, more solid, less full of empty spaces, then it's not like the comets we've actually seen up close. Either way, something's off and we need to figure out why this thing survived. Let's just get this out of the way. There are no aliens here, no secret plots, nothing like that. People always want to jump to wild ideas, especially since Oumuamua got everyone talking about possible artificial origins. But that kind of noise just distracts from the real puzzle. What we really have is an object that didn't behave the way our models said it should, and a bunch of scientists trying to make sense of it. It's a reminder that we don't know everything, and sometimes the universe just does what it wants, no matter how neat our theories look on paper. This kind of mystery is actually what science thrives on. You watch, you build your models, you try to predict what'll happen next, and when reality throws you a curveball, well, you go back and rethink what you thought you knew. That's how we've managed to piece together everything from gravity to quantum physics. But it takes some humility, because sometimes you just have to admit you were wrong. Sometimes the universe makes you start from scratch. 3IATLAS feels like one of those moments. Not a total game changer. Physics still works the way it always has, but it's a wake-up call. A hint that maybe our definition of a comet needs to stretch a bit when we start talking about visitors from other star systems. So here's what we'll do. We'll walk through what happened before Perihelion, what astronomers saw when the comet swung close to the sun, and what this all means for how we think about interstellar objects. We'll dig into the structure, the heat, and the growing suspicion that comets from other places don't follow the same rules as our local ones. We'll look back at comets that fell apart and why they did. We'll retrace how 3IATLAS was tracked, observatories on the ground, telescopes in orbit, data piling up night after night as everyone waited to see if it would hold together or explode. We'll talk about the models and the computer runs, the teams at NASA and across the country trying to predict what would happen. And then we'll face the awkward truth. When the predictions don't match what actually happened, we're missing something important. This story is about survival in the harshest conditions. An object from deep space that sailed straight through the sun's heat and came out the other side in one piece. Scientists watched, took notes, and now they're still arguing about how it managed to do that. The sun doesn't cut you any slack. Most comets get torn apart. 3IATLAS didn't. That's weird and it matters. It's not impossible, not magic, not breaking the laws of nature. But it's strange enough that our go-to explanations fall short. Each new bit of data just throws more questions into the mix. Even now, more than a year after Perihelion, nobody's totally sure what kind of visitor we just had. The debate keeps going, papers, conferences, late-night arguments, trying to pin down what makes 3IATLAS stand out. And if we can answer that, maybe we'll learn something new about the universe outside our own solar system. We're about to dig in, or at least we're going to give it our best shot. Part 2, the expected discovery. Let's start with what's normal. These days, discovering and tracking comets takes a lot of teamwork. Survey telescopes, space observatories, and hundreds of astronomers all pitch in, night after night, to map out the little wanderers drifting through our solar system. They work carefully and stick to a method, spot objects early, follow them, and figure out what they'll do as they close in on the sun. ATLAS, short for Asteroid Terrestrial Impact Last Alert System, runs out of observatories in Hawaii and Chile. NASA funds it, and the goal is simple: sweep the sky, night after night, and spot anything that moves. That means asteroids, comets, even objects that could one day cross paths with Earth. The system snaps multiple pictures of the same patch of sky over several nights, then compares them. Anything that budges gets flagged, and astronomers follow up. The idea behind ATLAS isn't rocket science, but making it work is a whole different story. There are 4 telescopes, each with half-meter mirrors, nothing huge, but paired with powerful cameras that can grab big chunks of the sky at once. When the weather's good, every telescope goes to work, taking picture after picture. Within a few hours, smart software checks each new image against older ones from days or weeks before. Stars are the background actors here. They don't move, at least not in any way you'd notice over a few nights. But things in our solar system, asteroids, comets, even spacecraft, they roam. They slide across that fixed starry backdrop. The software catches these shifts, automatically flagging thousands of moving blips every night. Most turn out to be things we already know about, cataloged asteroids, tracked spacecraft. But sometimes something unknown pops up. That's what happened on July 1st, 2025. Atlas picked up a faint, moving smudge. Nothing dramatic at first. New comets aren't rare. Most come from the distant Oort cloud or their old short-period regulars circling the sun again. The steps are the same every time. Calculate a rough orbit, give it a label, and alert the global astronomy community so others can check it out. This particular find happened at the Atlas site on Haleakala, Maui, a huge volcanic peak over 10,000 feet above the Pacific. Up there, you're above much of the turbulence and water vapor that messes with telescopes. The sky was clear, the air steady. A grad student from the University of Hawaii was on duty, running the usual observation routine when the automated system pinged about the new object. First step, make sure it's real. Cosmic rays sometimes zap the detectors, leaving phantom spots that look like faint objects, so you always double-check. Then, see if it matches anything already in the database. If it's genuinely new, pin down its exact position so other astronomers can find it too. After that, you send the discovery off to the Minor Planet Center at the Smithsonian in Massachusetts, the go-to place for all asteroid and comet discoveries. The first look showed a dim object, somewhere around magnitude 19 or 20, way too faint for the naked eye, but no problem for Atlas's cameras. It looked a little fuzzy too, which usually means comet rather than asteroid. They logged its spot in the sky and took another look a few hours later. It had moved. They sent the data to the Minor Planet Center. Within a day, telescopes in Arizona, New Mexico, and Chile were looking at it too. Each new observation sharpened the position. Every bit of data tightened up the orbit. When astronomers at the University of Hawaii and NASA's Jet Propulsion Lab started crunching the numbers on this new object, the orbit they found was a surprise. It wasn't elliptical like most things we see zipping around the sun. Nope, the trajectory was hyperbolic. That means the object's moving too fast for the sun to keep it tied down. It's not looping back around. It's just passing through, a true visitor from interstellar space. They checked the orbital eccentricity, which is just a fancy way to say how stretched out the orbit is. If it's between 0 and 1, you've got an ellipse. If it's exactly 1, that's a parabolic path, right on the edge of escape. But anything above 1, that's hyperbolic, and it means the object comes from beyond the solar system and won't stick around. For 3IATLAS, the early calculations landed at about 1.04, then later they dialed it in to around 1.037. That's not wildly above escape speed, but it doesn't need to be. It's enough. Enough to show this comet didn't form here. Enough to make it just the third confirmed interstellar object anyone's ever spotted. Only 3 ever. The first was 1I/Oumuamua back in 2017. That one was weird, long and skinny, moving in ways comets aren't supposed to. People argued for years over whether it might be artificial. Then 2I/Borisov came along in 2019 and looked like a regular comet, which was actually a relief. Maybe most interstellar visitors aren't as bizarre as Oumuamua after all. Oumuamua wasn't just a scientific oddball, it was a cultural flashpoint. Its shape, they think, was super elongated, maybe 10 times longer than it was wide. And it sped up as it left the sun, but with no visible outgassing, which comets usually show. That got people wondering, could it really be an alien probe? Avi Loeb, a well-known Harvard astrophysicist, even said we shouldn't rule that out. Most astronomers pushed back, suggesting natural explanations. Maybe it was made of nitrogen ice or had some other exotic chemistry going on. But the debate was loud, and suddenly, interstellar objects were in the public spotlight. Then there was Borisov. Honestly, it was almost boring. It looked like a comet, acted like a comet, and its spectrum showed all the usual stuff: water vapor, carbon monoxide, dust. Its core was a few hundred meters across, just like small comets from our own solar system. No strange acceleration, no odd shapes, just a garden-variety comet from another star. That was actually comforting. It hinted that most interstellar objects are probably just regular comets or asteroids, and Oumuamua is the weird one. Now there's 3IATLAS, and as soon as the word got out, observatories everywhere swung their telescopes in its direction. Astronomy, as a field, is pretty unique when it comes to sharing data. When something rare like this shows up, observatories don't keep the info to themselves. They share everything. Within days of Atlas spotting the comet, teams all over the world were planning who would look at it, with what instruments, and what they should measure first. Hubble, still going strong decades after launch, turned to catch it. Getting Hubble time is tough. Demand always outweighs what's available. But interstellar objects get bumped to the front of the line. They're only here for a short time. Miss your window and they're gone for good. Hubble's sharp eyes could grab detailed images and maybe even get a direct measurement of the comet's nucleus. And then there's the James Webb Space Telescope, the most powerful infrared tool we've ever built. Webb locked onto the comet, ready to measure its heat and composition in fine detail. Infrared light cuts through dust better than visible, so Webb could see deeper into the comet's coma and maybe even spot the nucleus itself. With its spectroscopy, Webb could break down the exact mix of gases flying off the comet: water, carbon dioxide, carbon monoxide, methane, ammonia, and even more complex organic stuff. All over the country, observatories jumped in: Lowell in Arizona, Keck in Hawaii, and the very large telescope in Chile, which, honestly, feels like half American with all the collaboration. They kicked off a coordinated effort to watch this new comet. Ground-based telescopes have a leg up in a few ways. For one, they're just bigger. The Keck telescopes each have a 10-meter mirror, which makes Hubble's 2.4-meter mirror look tiny. Bigger mirrors mean more light, which means you can see fainter things and pick up finer details when you split the light into spectra. There's also the flexibility. If the weather's good, you can observe every night. Space telescopes like Hubble or Webb have to book their time way in advance, juggling requests from all over. But on the ground, if something weird starts happening, like if 3IATLAS suddenly brightens or acts up, astronomers can swing their instruments over and catch it, sometimes in just a few hours. That's how astronomy goes these days. Machines spot something new, but people have to step in and make sense of it. Teams from all over share data, double-check results, and keep refining their models as more info rolls in. There's a rhythm to it, a kind of confidence that comes from decades of watching comets follow the same playbook. At Lowell Observatory in Flagstaff, the same place where Clyde Tombaugh found Pluto back in 1930, astronomers pointed their 4.3-meter Discovery Channel telescope at 3IATLAS. They wanted to see its spectrum, basically checking which colors of light the comet was absorbing or giving off. That tells you what it's made of. Molecules each have their own little signature. Water shows up one way, carbon dioxide another. With a good spectrum, you can figure out which gases are in the coma and even guess how much of each is in there. The early results, pretty much what you'd expect from a comet: water vapor, carbon dioxide, carbon monoxide, and a background of sunlight bouncing off all the dust swirling around. Nothing shocking, but the ratios caught their attention. There was a lot more carbon dioxide than water, kind of the opposite of what you usually see in comets from our solar system, where water leads the pack. Comets are messy little snowballs. They're full of water ice, frozen carbon dioxide, carbon monoxide, dust, and leftover bits from when the planets were forming. When one swings close to the sun, things heat up fast. The ice doesn't melt, it just skips right to gas, since there's no air pressure in space to let it become a liquid. That gas and dust billow out, wrapping the nucleus in a glowing coma and sometimes stretching out into a long tail, pushed away by sunlight and the solar wind. The science behind this is pretty solid. Ice in space doesn't get a chance to melt. It goes straight from solid to gas. As the sun heats the comet, molecules on the surface get enough energy to break free and escape as vapor. How fast this happens depends on how hot things get, which comes down to distance from the sun and what the surface is like. Water ice kicks in when the comet gets within about 3 astronomical units, AU, of the sun. Carbon dioxide wakes up farther out, around 4 or 5 AU. Carbon monoxide and nitrogen hang on even longer, staying active out past 10 AU. So as a comet makes its way towards the sun, different ices start to boil off at different points, each changing the show as it goes. We've got this process down. Spacecraft have flown by comets, landed on them, even brought back pieces. The Rosetta mission spent 2 years alongside Comet 67P, watching its activity change day by day. NASA's Deep Impact mission literally punched a hole in Comet Tempel 1 to see what was inside. Stardust grabbed samples from Comet Wild 2 and sent them all the way back to Earth for scientists to pick apart in labs. We know what happens when ice turns straight into vapor, sublimation on a comet. Gas jets shoot out, dust tags along, and we've got solid models to explain all of it. These models have been tested against the comets in our solar system. They hold up. That's why 3IATLAS's behavior at Perihelion totally threw astronomers for a loop. According to the models, it should have broken apart or at least done something dramatic. But it didn't. At first, 3IATLAS played by the rules. It grew a coma, just like you'd expect. Spectroscopy from telescopes in the US and Europe picked up water vapor, carbon dioxide, carbon monoxide, the usual suspects. Measurements of its brightness hinted at a nucleus somewhere between a few hundred meters and a few kilometers across. The range was huge, but that's par for the course with distant comets shrouded in their own dust and gas. Measuring a comet's nucleus is weirdly hard. All you see is that glowing coma, a puffball of gas and dust. The actual nucleus sits buried deep inside, tiny by comparison. To pin down its size, you need to look in wavelengths where the coma is less of a nuisance, usually infrared or radio. Or you build a model of the coma, estimate how much light it's adding, and subtract that to see what's left from the nucleus itself. For 3IATLAS, people guessed anywhere from 440 meters to 5.6 kilometers across. That's an absurd range, a factor of 10. If the nucleus was tiny, maybe half a kilometer, it had to be crazy active, venting gas from most of its surface. If it was on the large side, just a patch here or there would be enough to drive the coma. Either way, you end up with wildly different ideas about what this thing is made of and how it's built. As 3IATLAS headed toward the sun in the summer and fall of 2025, the activity ramped up. No surprise there. Get closer to the sun, soak up more heat, and the ice goes wild. The coma brightens. It was textbook behavior. Photometric data, just careful tracking of how bright it looked over time, showed that smooth, steady rise as it neared perihelion. No sudden flare-ups, nothing weird. Just a gentle climb, matching the idea of steady ice loss as it got warmer. Spectroscopic readings kept picking up water, carbon dioxide, and carbon monoxide, but the carbon dioxide stayed unusually high. Astronomers marked the calendar, perihelion on October 30th, at a distance of 1.4 AU. That's about 210 million kilometers from the sun, near Mars's orbit. Not super close by comet standards, some skim right past the sun, but close enough for serious heat and stress. If the nucleus was going to fall apart, this would be the moment. Take Comet Encke, for example. It swings into just 0.3 AU every few years and shrugs it off, probably because it's a tough, rocky relic with almost no ice left after thousands of trips. Hale-Bopp got as close as 0.9 AU in '97 and survived easily, but that thing was a monster, up to 80 kilometers across. Gravity alone helped keep it together. Most comets that come within 1 to 2 AU survive. Not all. The ones that break up are usually weak, loose rubble piles or icy bodies held together by little more than hope. So everyone wanted to know, which camp did 3IATLAS belong to? History said we should expect something at perihelion. Maybe a burst of brightness as fresh ice came into play. Maybe a little fragmentation, some bits breaking free. Maybe some wild jets. All normal stuff. Total destruction. Not likely, but not out of the question. Some comets just can't handle the heat. The outer layers expand, the inside stays frozen, and the whole thing cracks open. If 3IATLAS was especially fragile or weirdly built, Perihelion could have ripped it apart. Observatories got ready for anything. People lined up images before, during, and after perihelion. Spectroscopes would watch for any changes in the gases. Photometry would keep tracking the brightness. If the comet broke up, telescopes would chase down the fragments. If it didn't, the plan was to study every change in activity or in the look of the coma. Either way, they were ready to catch the story as it happened. Excitement ran high. Interstellar objects don't show up often, and everyone is a rare shot at studying something straight from another star system. Compare it to our local comets. Test your favorite theories about how planets form. There's a lot riding on these visitors. The scientific community was ready. Over at NASA's Jet Propulsion Lab in Pasadena, a team was deep into simulations, trying to figure out what would happen when the object hit perihelion. They used tried-and-tested comet models, heat moving through the core, how different ices turn to gas, where jets might erupt, how the whole thing might crack under the stress. They tuned these models using data from hundreds of solar system comets. The simulations didn't spit out one clear answer. Everything depended on what the thing was made of and how it was put together. If it was full of ice and pretty porous, it would probably break apart. If it was heavier on rock with a tough crust, maybe it would make it through. The catch: no one really knew what was inside, not before perihelion. Then perihelion came. From Earth, 3IATLAS slipped behind the sun in late October. For days it vanished, way too close to the sun's glare for telescopes to see. Astronomers call this solar conjunction. It happens all the time. You lose sight for a bit, then your target pops back out. You just have to wait. This time, the blackout lasted 5 days. 5 days when the comet was closest to the sun, taking the most heat, and no one could watch. They knew where it was. Orbital mechanics made sure of that, but whether it would survive, that was anyone's guess. All they could do was wait, eyes on the sky, hoping 3IATLAS would reappear on the far side. November 4th, scopes in the US and Chile picked it up again. There it was, still shining, still with a coma. First sign it survived. If it had blown itself to dust, there might have been nothing left. But just seeing it wasn't enough. Broken up comets can still have comae from their pieces. The real question, was the nucleus still whole or had it shattered? Getting that answer needed sharper images and a close look at the data. As soon as 3IATLAS cleared conjunction, astronomers jumped in. They measured its brightness, the shape of its coma, spectra, position, speed, the works. They wanted to know exactly what perihelion had done. Then came the first surprise. The comet was still there. Not just visible, but solid. No big fragments. The coma looked much like it did before, maybe a bit livelier, but nothing wild. Brightness ticked up, more outgassing probably, but no sudden outburst or flare. Nothing to suggest a hidden pocket of ice had exploded into space. That's weird. Not unheard of, but strange. Most comets change after perihelion. Even the tough ones usually shed some material or sprout new jets as the sun warms up new patches. 3IATLAS. It looked steady, strangely steady. Hubble's images showed a tight, unresolved nucleus surrounded by a perfectly even coma. No fragments, no lopsided jets, no dust tails hinting at active spots. The symmetry was almost unsettling. Real comets are messy, outgassing isn't uniform, different areas have different stuff, and as the nucleus spins, you usually get all sorts of structures: jets, fans, expanding shells. This comet's coma, smooth, even. Like the whole surface was outgassing at the same rate, or maybe it was just leftover dust from earlier. Scientists didn't jump to conclusions. Interesting, a NASA researcher said at a conference. Suggests a robust nucleus. Another astronomer from Arizona wrote that the lack of fragmentation implies either a rock-dominated composition or an unusually coherent internal structure. Careful words, as you'd expect. Still, under all that caution, there was a quiet question nobody wanted to voice, at least not yet. What if this object isn't just a comet? Not in the sense of being artificial, there was no evidence for that, but in the sense of being something fundamentally different from the icy, fragile bodies we're used to studying. Something built by different processes in a different stellar environment. Something that survived the journey through interstellar space and arrived here with properties we didn't expect. The data kept coming in, and the data kept refusing to settle into a comfortable explanation. Part 3. When the data refused to behave. Science is all about tweaking and adjusting. You watch, you guess, you check if your guesses hold up when new facts roll in. If they don't, you go back, fix the model, and try again. It's never really tidy, just a big, messy loop. But most of the time, it works. Then you hit a wall. Sometimes, the new facts don't just poke holes in your models, they blow up the whole way you're used to seeing things. That's when science gets a little uncomfortable. Right after Perihelion, as observatories everywhere kept tracking 3IATLAS, things started to look off. The data just didn't match what you'd expect from a typical comet. Not even close. The first big red flag, structural integrity. Let's talk about perihelion and thermal shock for a second. At 1.4 astronomical units from the Sun, you're dealing with about half the solar energy Earth gets. That sounds gentle, but for something that's spent forever in the deep freeze of interstellar space, even that is a serious heat jolt. Normally, a comet's surface heats up fast as it swings in close to the Sun. Ice turns straight into gas. Pockets of gas build up under the surface, especially if the nucleus is full of holes and gaps, which honestly most comets are. Eventually, that gas has to escape. Sometimes it blasts out in jets, sometimes it just cracks things open. The outer layers want to expand from the heat, but the cold, rigid inside holds them back. That's how comets tend to break apart. History backs this up. We've seen it again and again. Shoemaker-Levy 9 fractured into more than 20 pieces before it crashed into Jupiter in '94. Linear fell apart in 2000. ISON shattered at perihelion in 2013. Atlas, different comet but easy to mix up, split in 2020. It's almost routine. Sure, some comets survive their close sun encounters. We see plenty make it around for multiple laps, but they rarely come through unscathed. Chunks break off, the core shrinks, jets get wilder as weak spots bust open. But 3IATLAS, nothing. No obvious damage. Hubble's high-res images, analyzed by NASA folks in Maryland, showed a tight, clean point of light at the center, wrapped in a perfectly even coma. No splinters, no cracks, nothing weird in the coma's shape. If there were jets or breakups, you'd spot it, but no. So people started digging into the size and mass. Maybe 3IATLAS is just huge, big enough that its own gravity keeps it together, but the numbers were all over the place. Some observations pointed to a nucleus as small as 440 meters, others as big as 5.6 kilometers. That's a massive difference. If it's small, say half a kilometer, gravity alone shouldn't cut it. The thing should be falling apart under stress. Comets are fragile, held together by crumbly ice and rock. Not exactly sturdy stuff. If it's big, several kilometers across, then yeah, staying in one piece makes sense. But then the brightness doesn't line up. A big nucleus should be brighter, unless it's got an unusually dark surface. And comets aren't known for that. Researchers at JPL ran a bunch of simulations, trying to figure out what would keep a comet like this stable at perihelion. The only models that worked needed either a huge, nearly inactive nucleus, or one that's mostly rock with hardly any ice. Both situations could explain the lack of breakups, but neither fit everything else people were seeing. So the mystery just got deeper. Now about that thermal emission puzzle. When the James Webb Space Telescope captured infrared images of 3IATLAS near perihelion, astronomers at the Space Telescope Science Institute found something strange. The temperature spread just didn't fit the usual pattern. Normally on a comet, the side facing the sun heats up a lot more than the night side. Because comets turn slowly, the day side soaks in heat, and you end up with a hot spot right under the sun. That's the standard model. But 3IATLAS didn't follow these rules. Instead of a clear hot spot, the heat seemed to be smeared out, more even than expected. It looked like the surface was sharing heat around much faster than simple rotation could explain. that hinted at either really high thermal conductivity, the stuff inside the comet moving heat through itself quickly, or maybe something was odd about how the comet spun or which way it was tilted. Here's the thing: comets aren't supposed to be good at conducting heat. Ice, especially when it's full of dust and holes, acts like an insulator. Most comets barely let heat seep in, which is why their insides can stay frozen solid even while the surface is boiling off gas. If 3IATLAS actually moves heat quickly through its core, that means it's made of something pretty different from your typical comet. That led some researchers to wonder if this thing is more like an asteroid, mostly rock, not ice. Rock transfers heat a lot better than ice does. If you took a rocky core and just sprinkled a little ice over the surface, you get a thermal profile kind of like what they saw. But then, why does it have a coma? Why is it venting gas? Asteroids almost never do that unless they get hit or spin so fast they fling off dust. Neither seem to fit here. The spectroscopic data just made things weirder. Observatories in Arizona and Hawaii, plus some space telescopes, picked up water vapor, carbon dioxide, and carbon monoxide in the coma. The mix was strange, more carbon dioxide than you'd see in most comets from our solar system. That matched up with the idea that 3IATLAS formed somewhere else, maybe in a place where carbon dioxide ice hangs around longer than water ice. But after perihelion, things shifted again. Suddenly, there was a lot more water vapor relative to carbon dioxide. That usually means sunlight has dug into deeper layers of the nucleus, exposing new stuff. Comets are layered, after all. The outer shell gets baked by the sun over time, and once you crack it, you reach fresher ices, which changes what gases escape. Except in this case, there was no sign the crust had broken. No fragments flying off, no big outbursts. So how did the deeper ice get exposed without the surface falling apart? Maybe the comet's crust is super porous, letting gas bubble up from the inside without breaking through. That happens with most comets, but the process would have to be much more efficient here to explain the gas ratios without any surface drama. It pushes the limits of what the models allow. Another idea: maybe 3IATLAS has circled close to other stars before, getting roasted and losing its most delicate layers long ago. That would make it tougher and less likely to shatter. But most interstellar objects get kicked out of their home systems pretty early, during planet formation. They probably don't get a lot of close passes before getting booted into the void. So that theory seems like a stretch. And then there's the rotation puzzle. Comets are usually tumbling all over the place, tossed around by their own outgassing jets. You can figure out the spin by looking for regular changes in brightness as sunlight hits the lumpy surface at different angles. 3IATLAS didn't show those patterns. Its brightness stayed pretty steady. That could mean it's spinning really slowly, maybe days or weeks for a full rotation, or that it's unusually round so spinning doesn't change how much sunlight it reflects. Both options are odd. Slow rotation is weird because it should spin things up over time. And a round comet, that's not what you expect from a pile of ice and dust clumps stuck together. Comets are usually odd-shaped, not smooth spheres. A few astronomers started slipping the phrase anomalously coherent into their talks and papers. Not artificial, not engineered, just holding together in a way comets usually don't. The nucleus wasn't falling apart like you'd expect. Its temperature stayed more even than normal. It spun more steadily than a typical comet. On their own, each weird trait had some natural explanation. But when you stacked them all together, it stopped making sense. At least, not in a way that felt likely. Something about 3IATLAS just didn't fit with the comets we know. Then the energy budget problem showed up. A team at the University of Maryland and NASA Ames ran the numbers. They looked at how much gas 3IATLAS was kicking off, based on its brightness and spectroscopic data. Then they calculated how much sunlight it should be soaking up, factoring in its size, distance from the sun, and how reflective it was. The answers didn't line up. The comet was releasing more gas than solar heating could explain, especially since there weren't any obvious jets or hotspots. So where was the extra energy coming from? Solar heating is the go-to answer. Comet activity runs on sunlight. But if the nucleus was small, it would need to absorb and use sunlight with almost perfect efficiency, losing almost nothing to space. That's barely within what we know comets can do. If the nucleus was big, the energy math looked better. But then it should have been much dimmer, unless its surface was weirdly dark. That didn't fit the spectroscopic data either. Some researchers floated the idea that 3IATLAS had extra heat inside, not from nuclear reactions, not chemical but radiogenic. Comets always have a little radioactive material in them. Normally, that heat is a drop in the bucket compared to sunlight. But if 3IATLAS formed somewhere rich in certain isotopes, that internal heat could actually matter, especially deeper down where sunlight can't reach. No one had hard evidence for extra radioactivity. Just kept the math from falling apart without getting too wild. Another theory, maybe the comet was holding onto stored heat. Maybe it passed close to a hot star or through a warm dust cloud on its trip between the stars and was still cooling off. That felt like a stretch, given how long those journeys take, but no one could rule it out for sure. By late 2025 and early 2026, the published papers got cautious. They stuck to the facts. They listed possible explanations. They flagged the unknowns, but you could feel the unease underneath. The models weren't snapping into place. Nothing was totally impossible, but something about this object just didn't add up. At a December 2025 conference in Texas, a senior NASA scientist wrapped up a talk on 3IATLAS with a slide that said, "More observations needed." Basically, we don't know what this thing is. Someone finally asked the question everyone had been thinking. Is it possible this isn't a comet at all? The scientist paused, picked his words. All available evidence indicates natural origin, but the classification may need refinement as we learn more about the diversity of interstellar objects. In plain English, it's not artificial, but it doesn't really fit the comet label either. After the talk, people mingled in the halls and over coffee. Some astronomers said the whole thing was overblown. Get better data, tweak the models, it'll all make sense. Others were stumped. A few admitted, quietly, that in their whole careers, they'd never seen a natural object as weird as 3IATLAS. Hanging over everything was the big, awkward truth. This thing made it through Perihelion in one piece. We honestly don't know how. So let's get into what the data actually said, because the real story in the details. The rotation problem stands out. When Rosetta got up close to Comet 67P, it clocked the nucleus spinning every 12 hours or so. As the comet got nearer the sun, all that outgassing sped up the spin just a bit, what scientists call jet torque. That makes sense. Gas shoots out one side, pushes back, and the comet spins faster. For 3IATLAS, astronomers at the University of Hawaii and NASA's Ames Research Center tried to measure rotation by tracking how its brightness changed over time. Classic move for figuring out a comet's spin. They took image after image, night after night, measuring how bright the nucleus and coma looked. If the nucleus is lumpy or weirdly shaped, you'd expect the brightness to rise and fall as it rotates, brighter when more of it faces us, dimmer when less does. But the data, nothing obvious, no clear repeating pattern. The brightness wobbled, sure, but it was all over the place. No steady rhythm, no sign of rotation. What's up with that? Maybe the rotation's super slow, so slow they didn't catch a full spin in their window. Or maybe the nucleus is almost a perfect sphere, so spinning doesn't change how much light we see. Or maybe there's something else going on, like outgassing that's so messy and unpredictable, it just drowns out any sign of rotation. And honestly, none of those answers feel quite right. Slow spinners are rare. Small objects in space usually get spun up by collisions and jets. A nearly perfect sphere. Unlikely, since weak gravity can't easily mold a comet into something that smooth. And if outgassing is wild enough to hide the rotation, why don't we see obvious jets or other hints of that chaos? Then there's the polarimetry, which just made things weirder. Polarimetry looks at how light waves line up after bouncing off comet dust. Usually, sunlight scatters off those particles and gets partially polarized, meaning the light waves tend to move in certain directions, not just any which way. How much and in what direction depends on the dust's size, shape, and makeup. Scientists pointed the Nordic Optical Telescope in the Canary Islands and the Keck Observatory in Hawaii at 3IATLAS's Comet and measured the polarization. The result? Weird. The curve was flatter and more neutral than what we see in regular comet dust. It's like the dust grains were either much bigger, more spherical, or just made out of something totally different. Most comet dust is a jumble of silicates and organics, messy, fluffy stuff that gives a standard polarization signal. But if 3IATLAS's dust is more compact, coated with something strange, or made of different minerals, you'd expect it to scatter light in a new way. All of this circles back to the idea that cosmic rays change the surface over time. Out in interstellar space, 3IATLAS spent ages getting bombarded by high-energy particles. That could mess with its chemistry, organic molecules turning into tarry goop, silicate grains changing structure, icy layers turning into crusts. Any of those things could create dust with odd optical tricks, and that just adds another layer of mystery to the whole story. We just don't have enough data to prove this. Unless we get samples back from a mission or send a spacecraft in for a close look, we have to rely on remote observations, and honestly, those only get us so far. There's plenty of uncertainty in what we can infer from a distance. The problem with the comet's energy budget actually got worse as scientists fine-tuned their models. Here, why that matters. When a comet releases gas, it doesn't use all the solar energy it receives. Some sunlight gets absorbed and heats the ice, some just bounces off, and a chunk of that absorbed energy seeps into the nucleus instead of turning ice straight into gas. Only a slice, maybe 10% to 50%, depending on what the surface is like, actually goes into turning ice into vapor. For 3IATLAS, the amount of gas it was shedding told researchers how much energy was going into that process. The NASA Goddard team worked out how much sunlight the comet was getting based on its distance from the sun and its likely size. Their calculations pointed to a weird conclusion. To match the observed outgassing, the nucleus would either have to be much smaller than expected, so more of the sunlight goes directly into sublimation, or it would need to be crazy efficient at turning sunlight into gas, meaning barely any energy gets wasted. Neither answer really worked with other things we'd seen. If the nucleus was that small, it probably would have fallen apart from the heat near the sun. If it was that efficient, you'd expect a surface that's perfect for shedding gas, dark, porous, showing off lots of fresh ice. But observations showed a smooth, steady coma. No wild jets, no dramatic outbursts. Not what you'd expect from a surface working overtime. Scientists at the Southwest Research Institute came up with what they called the layered crust model. Basically, they think 3IATLAS might have a thick outer shell, built up from radiation-altered organics and compacted ice, that acts like insulation. Under that, there's a layer of ice packed with more volatile stuff, protected during the comet's long trip through interstellar space. When the sun heats things up at perihelion, the energy finally makes it through the crust and hits that volatile layer, causing intense sublimation below the surface. The gas then bubbles up through tiny pores and escapes, creating the coma we see without cracking the crust wide open. This idea ties a lot of loose ends together. The crust keeps the whole thing stable, the hidden layer explains the jump in activity after perihelion, and subsurface heating would make the energy budget work out better than if everything happened right at the surface. Still, it's just a hypothesis. There's no direct proof for any crust or layers. It fits the facts, but until we can drill into the nucleus, not happening anytime soon, it stays in the realm of educated guesswork. Then there's the weirdness in the coma itself. High-res images from Hubble and telescopes in Hawaii and Chile showed a coma that was almost eerily perfect, smooth, round, and stable. Normally, comets are messy. Their comae break into shells, shoot out jets, show arcs and streamers, all thanks to uneven surfaces, spinning nuclei, and patchy heating from the sun. But 3IATLAS, its coma looked like something out of a textbook, just a neat circular dust cloud getting brighter toward the center, and that's about it. No obvious structure, just some faint gradients matching what you'd expect if dust drifts out from the nucleus at a steady speed. Ideal in theory, but real comets almost never behave so politely. And that's weird. Nature doesn't like symmetry. Real comets have rough surfaces. Their spin axes are tilted every which way, and their gas jets come and go as different spots heat up. For 3IATLAS to keep up this perfect coma through its closest approach to the Sun and beyond is hard to explain. Maybe it's outgassing evenly all over, which is a stretch, geometrically. Or maybe we're just seeing old dust from earlier activity, not fresh stuff from ongoing outgassing. But that second idea doesn't really fit the spectroscopic data, which says the comet's still producing gas. So, the mystery holds. A group of UCLA researchers tossed out the idea that maybe 3IATLAS spins really fast. So fast that sunlight and shadow whip across its surface over and over, all in a single day. If that's true, rapid rotation would smooth out any lopsided features, leaving behind a coma that looks nice and even. But then, spinning that quickly should make the object's brightness flicker, and astronomers haven't seen that. Plus, a weak, loosely held together nucleus should just fly apart under all that stress. That didn't happen either. Every time someone tried to explain one weird thing about 3IATLAS, it just made something else stranger. It felt like trying to put together a puzzle, but the pieces came from a bunch of different boxes. By early 2026, the floodgates had opened, dozens of papers, each one picking apart some detail of 3IATLAS's swing past the Sun. They were careful, thorough, even a little cautious. But when you step back, you see the real story. This thing doesn't fit any of the usual labels. It's not a regular comet. It's way too stable and holds together too well. It's not an asteroid either. Way too much outgassing, way too obvious a coma. It sits somewhere in between, or it's something totally new. All over the country, from Arizona deserts to mountaintops in Hawaii and observatories in Maryland, astronomers kept their eyes on 3IATLAS as it slipped away from the Sun. Its brightness faded, its activity dropped. Week by week it grew fainter, tougher to track. The clock was ticking. Soon it would vanish from view. Meanwhile, data piled up. Thousands of images, spectra, light curves, precise positions to pin down its orbit. All the little clues gathered during those frantic months when this interstellar visitor came close enough for us to get a good look. Maybe somewhere in that mountain of data, there's an answer, a detail that finally explains what makes 3IATLAS so odd. Or maybe the answer just isn't there. Maybe all we have is a question, and we'll have to wait for the next traveler from another star before we can really start to understand what these objects are like. One thing is clear, though. 3IATLAS made it through its closest approach to the Sun in one piece. By the usual rules, it should have cracked up, split apart, or shown signs of stress. But it didn't. That's the heart of the mystery. Everything else, the temperature, the weird rotation, the coma, the energy, the way it handles light, comes back to this. How did an interstellar comet survive a close brush with the Sun without falling apart? Whatever the answer is, it's still just out of reach. Part 4. Scientific Silence and Human Limits. There's a special kind of silence in astronomy. Not the silent vacuum of space. Not really, since space isn't truly silent, just empty of sound waves. I mean the silence of not knowing. The kind you feel when the data just sits there, stubborn, refusing to come together into any real story. The silence you get at 3 in the morning, scientists hunched over their screens, running yet another simulation, hopping something will finally click, and coming up short again. That's where things stood with 3IATLAS as winter faded into spring in 2026. People kept watching. Telescopes followed the comet as it slipped farther from the Sun, back out toward the edge of the solar system, on its way to interstellar space. Every week brought fresh numbers, brightness, spectra, pinpoint positions to nail down the orbit. The data was good, really good. The kind of stuff astronomers dream about when a rare visitor from another star drops by. But here's the thing. Good data doesn't guarantee clear answers. Nobody talks much about what happens between gathering data and actually understanding anything. That space is messy, uncomfortable. It doesn't make for neat headlines or satisfying stories, but honestly, most science happens right there. You get your data, you crunch the numbers, you compare what you see to your models. When the numbers line up, great, You write your paper and move on. When they don't, you start poking at everything. Maybe there's noise in the data, an instrument glitch, a calibration slip, some atmospheric quirk you didn't quite catch. Maybe the models are off, bad assumptions, missing physics, shortcuts that don't hold up. Usually, with enough effort, you find the problem. The data gets cleaner, or the models get smarter, and finally, things make sense again. But not always. Sometimes the data looks rock solid and the models just can't keep up. That's exactly where 3IATLAS left people in early 2026. Researchers all over the US and Europe kept at it. They tried to map how the object rotated, but the brightness kept changing in weird, non-repeating ways. They measured how much gas was coming off, and sure, the numbers dropped as it moved away from the sun, just like you'd expect. But the drop didn't match the usual patterns for comet activity. They scanned for fragments, wondering if maybe the thing had finally cracked apart, weeks or months after its closest approach. Some comets do that, thermal stress splits them, but only after a delay. No luck. 3IATLAS stayed in one piece. Inside the astronomy world, the tone started to shift. Right after Perihelion, there was this mix of excitement and confusion. By the middle of 2026, confusion was winning. Papers started coming out with careful titles like Unusual Thermal Properties of Interstellar Object 3IATLAS or Structural Coherence of 3IATLAS, Implications for Interstellar Comet Populations. Those titles were polite. They asked questions instead of stating outright that something was wrong. But it was obvious. This object didn't fit the comet mold. Part of the trouble is just definition. What's a comet and what's an asteroid? The old rule was simple. Comets have comets and tails, asteroids don't. But now things are messier. Some asteroids give off gas. Some comets barely do anything. You get active asteroids, dead comets, and objects that switch back and forth depending on where they are. And with interstellar visitors, the labels get even slipperier. So far, we've only seen 3 confirmed ones. Oumuamua looked like an asteroid but sped up like a comet without any visible outgassing. 2I/Borisov acted just like a regular comet. 3IATLAS had activity like a comet, but held together like an asteroid. Trying to squeeze these weirdos into boxes built for solar system bodies might just be the wrong move. Maybe we need new categories. Maybe interstellar objects come in flavors we haven't even imagined yet, shaped by places and histories we know nothing about, because all that happened around distant stars with different chemistry. Changing these ideas isn't easy. Science tends to be conservative, and that's not a bad thing. You don't toss out a framework that works every time something odd shows up. Usually, you try to stretch the current models, add a bit more complexity, or find some new mechanism that still fits inside known physics. A bunch of teams gave it a shot. Some researchers at the University of Arizona tossed out the idea that 3IATLAS might be a rubble pile comet, basically a loose cluster of rocks and ice chunks, all held together by weak gravity and friction. Rubble piles aren't as fragile as you'd think. The bits can shift around and settle, soaking up stress instead of snapping apart. That could explain how it survived whipping so close to the sun. But here's the catch. Rubble pile models usually say that as a comet gets hit by jets of gas venting out, it should start spinning faster over time. 3IATLAS didn't do that. Its spin stayed steady, almost weirdly so. Over at NASA's Jet Propulsion Lab, another group suggested maybe the comet's nucleus had more rock than ice. Think of ice just filling in the cracks between rocks. That would make it tougher than a comet made mostly of ice. Rock doesn't vaporize in sunlight, and it gives the whole thing a sturdier skeleton, something that can hang together even as the ice disappears. That idea helped answer the question of why the comet didn't break apart, but it made the energy math messy. Rock doesn't soak up or move heat the same way ice does. You'd expect to see different patterns in how it glows in infrared, and a rock-heavy comet shouldn't throw off as much gas. Yet 3IATLAS had a pretty lively coma, plenty of gas and dust surrounding it. Then the European Southern Observatory team threw in another idea: cosmic rays. Out in interstellar space, 3IATLAS would have spent ages getting bombarded by high-energy particles, which change the surface chemistry and texture. That could build up a crust, a kind of tough, processed shell that's less volatile than the untouched stuff inside. The crust could help the comet survive its close call with the sun, while deeper layers still held ice that could escape through cracks. It all fit together in a satisfying way. This idea tied up a lot of loose ends. The trouble is, it's hard to prove. We don't know exactly what's on the comet's surface. Our telescopes can pick out gases in the coma, sure, but not the solid stuff deep inside. By summer 2026, the scientific papers all started to sound the same. Interesting, but still guessing. People shared data, talked through a bunch of theories, and always ended by asking for more observations, better models. That's just science, especially with something so new. But behind the scenes, at conferences or in private chats, you could feel a shift. Scientists were starting to admit it. Maybe we'd hit a wall. You can only learn so much from far away. If we really want answers about 3IATLAS, we need to go there. Fly a spacecraft out, snap close-up photos, take direct measurements, maybe even land on it. That's not likely to happen. These interstellar objects don't hang around. By the time we spot one, plan a mission, build the probe, and launch, it's already on its way out. 3IATLAS will be long gone by the time anyone's ready, and within a decade or so, it'll be so far away that even getting a signal to it would take forever. There are ideas on the drawing board: rapid response mission, spacecraft ready to launch at a moment's notice, or crazy fast propulsion like solar sails or nuclear rockets. But nobody's building them. Nobody funding them either, unless something big changes. So 3IATLAS will slip out of the solar system, taking all its secrets with it. We'll keep watching until it's too faint to see, probably late in the 2020s. After that, the data gets filed away. Scientists will keep picking through it, publishing papers, running simulations. But the comet itself will be gone, drifting into the dark between the stars. There's something a little sad about that. Feels like a chance missed. We had a visitor from another solar system. We watched, we measured, we learned a lot, but not enough. Somehow, it survived where we thought it wouldn't, and now we're left with half answers and more questions. Not knowing hits everyone differently. Some researchers get frustrated, itching to crack the puzzle but always coming up short, like a word stuck on the tip of your tongue. Others just feel humbled, reminded that the universe doesn't owe us answers and is always a few steps ahead of our theories. And then there are those who feel inspired by the mystery itself, proof that there's still plenty left to discover out there. March 2026, Arizona. The dome was freezing even with the heaters going, and outside the temperature had sunk below zero. The air was thin at 7,200 feet. Each breath felt like it barely counted. But the sky, absolutely perfect. The Milky Way poured overhead, so bright it almost didn't seem real. She'd been in this from the start, part of the whole campaign to watch 3IATLAS as it drifted closer to the edge of what her telescope could catch. 3 papers bore her name: thermal properties, spin state, structural stability. She knew the data like old friends. She could spot the comet's spectral lines at a glance, name its place in the sky without checking the charts. Hundreds of hours spent poring over images, always chasing that one extra detail. Tonight felt different. Maybe this was her last shot. The comet had dimmed to magnitude 23, so faint, really, only a big telescope could even hope to see it. Give it another few weeks and it'd vanish for good. No second chances. She set up the telescope, lined it up, started the exposure. The camera would gather photons for as long as she let it. Minutes, hours. That's how you see things this faint. Just wait. You have to sit there in the cold, listening to the steady hum of the tracking motors. Watch the image crawl across the screen, pixel by pixel. Wait. Later, when she talked about it on an astronomy podcast, someone asked how it felt to see 3IATLAS slip away. You spend months with an object, she said. You get to know it in this weird, intimate way. You know its brightness curve. You recognize its spectral lines. You can predict where it'll be in the sky each night. And then it's gone, just gone, back into the dark. And you realize you'll never know some of the things you wanted to know. You'll never get definitive answers to some of the questions. That's the hardest part, not knowing, and knowing you'll never know. Her voice changed a bit then, not exactly sad, but there was something like acceptance in it. Resigned, but with a hint of awe, as if she'd grown used to not knowing but still felt the loss. She paused, then added, "But that's what keeps you going. Maybe the next one, maybe when the next interstellar visitor shows up, we'll figure it out. Or maybe we'll just end up with more questions. Either way, we'll be ready." That's science in a nutshell. You don't chase certainty. You chip away at the unknown bit by bit, even when the universe refuses to play along. The data's messy. The models never quite fit. You keep going anyway. Over in California at NASA's Jet Propulsion Lab, a group of scientists met in April, one of their post-mortem meetings, though 3IATLAS was still out there, just no longer within reach. They sat around a table with the San Gabriel Mountains outside the window, pulled up all the data they'd scraped together and tried to make sense of it. That meeting dragged on 6 hours. Thermal models, structural stability, spectroscopy, orbits. Everyone was careful to separate what they actually knew from what they'd guessed. Everyone admitted what was still up in the air. In the end, they managed a list, nothing fancy, just the facts. 3IATLAS was an interstellar comet. It made it past the sun in one piece. Its thermal behavior was strange, nothing like most comets from our solar system. Carbon dioxide showed up in higher amounts than water. The coma looked weirdly symmetrical and stable. The size? Still a big question mark. Same with how it spun. That was all they had. No big theory, no clean story tying everything together. Just a handful of observations and a bunch of open questions. One of the senior scientists, 30 years studying comets, put it plainly. "We saw something we didn't expect, we documented it carefully, and now we have to accept that we don't have all the answers. Maybe we never will, but the data is good. The next team or the team after that, they'll have this to build on." That's how progress works. Incrementally, sometimes frustratingly slowly, but it does work. There's something almost peaceful about that kind of acceptance. No raging at the universe for being confusing. No frantic need to pin down an answer. Just this quiet recognition. Science moves forward in tiny steps, not in wild leaps. Each piece builds on the last. 3IATLAS didn't blow up what we thought we knew about comets. It made things messier. It forced us to admit, hey, comets from other star systems don't always play by the rules our local ones do. Turns out, there's way more variety out there than we guessed. Surviving a close pass by the sun, perihelion, is rare, but it happens. Even under conditions we're still struggling to understand. These are small insights. They don't land on the front page. They don't flip cosmology upside down. But they matter. They move the science forward. They lay the groundwork for sharper observations, better models, smarter missions down the road. Already, 3IATLAS is showing up in grad student theses. Young researchers are building new models that try to fit the strange stuff we saw in this object. They're testing ideas about cosmic ray damage, tough outer crusts, rock-heavy cores. Some models will miss the mark. Some might get halfway there. Maybe one or two will really nail it. But every one of them inches us closer to understanding what these interstellar wanderers can be. Over at the University of Maryland, a PhD student is deep into building a thermal model that includes heating from long-lived radioactive stuff inside the comet. The goal? Figure out if that extra heat on top of sunlight could explain all the gas we saw blowing off, without having to assume the comet is somehow bizarrely efficient at turning ice to vapor. The model is a beast, with a ton of variables that need to be pinned down by real data. It'll take months to finish and test. And when it's done, it's just one idea among many, waiting for the next round of observations to confirm or contradict it. Meanwhile, in Texas at the Southwest Research Institute, another team is simulating what millions of years of cosmic ray bombardment do to the ice in these objects. They're using particle accelerators to blast ice samples with high-energy protons, tracking how the ice's structure and strength change, how its appearance shifts. Each experiment is slow, days to set up, days to run. But bit by bit, they're building up a database that future scientists can use to compare with actual interstellar comets like 3IATLAS. None of this gives quick answers. Science almost never does. But this is what it looks like, chipping away at a mystery, one careful experiment, one observation at a time. And honestly, the universe doesn't care about our deadlines. Some mysteries take their time unfolding. Some might never really resolve at all. That gap between seeing something new and actually understanding it, it can stretch for years, decades, even longer. There's a certain silence you get in astronomy, and it's tough to put into words unless you felt it. It's not the silence of space itself. There's no sound there, obviously. It's the silence in the data, when you've pulled together every observation, wrung everything out of your images, built model after model, and still, you're left with big questions. It's the silence at the end of a conference day, sitting in a room with a whiteboard full of equations and sketches, realizing you've hit the wall. Technology and theory can't take you any further right now. The next step needs something you just don't have yet: a better telescope, a smarter algorithm, more data, or an idea nobody had. But that silence isn't empty. It's heavy with possibility. Someone someday will have the breakthrough or the tool that finally cracks it open. But for now, you're camped out at the frontier, and you have to be okay with not knowing everything. 3IATLAS made it through its close brush with the sun. We watched it, we measured it, we tried to figure it out. Now it's drifting out of reach, and we're left with the usual in science: a patchwork of knowledge, guesses that might change, and that big, open question: what's still out there, waiting for us to find it? The object doesn't care about us or our questions. It just moves through space, carried along by gravity and momentum, totally indifferent to whether we ever figure it out. Give it a few million years and maybe it'll swing by another star. Maybe that star pulls it in and it spends the rest of forever circling a new sun. Or maybe not. Maybe it just keeps drifting, a wanderer with no destination, lost in the galaxy. We only got a short window to see it, just those few months when it was close enough and bright enough to actually study. We did what we could, pointed our telescopes, gathered data, and then it was gone. The window closed and the object moved on. That's how astronomy goes. We watch, but we're always on the outside. We measure, we analyze, we try to understand, but we can't reach out and grab these things. When they leave, we stay put. All we can do is wait for the next one, and the next after that, slowly piecing things together over years, decades, lifetimes. And honestly, maybe that's the whole point. Maybe the process matters more than any destination, if there even is one. The late nights at the observatory, arguing at conferences, writing careful papers that push our knowledge a little further. The grad students who give years to a single problem. This slow, shared effort to make sense of the cosmos, it's what keeps us going. 3IATLAS showed us something new. Interstellar comets can survive perihelion in ways we didn't expect. It poked holes in our models and reminded us not to assume the rest of the galaxy works just like our solar system. These aren't complete answers, but they're important lessons. And it reminded us again that the universe loves surprises. No matter what we think we know, there's always so much more we don't. Realizing that isn't weakness, it's wisdom. Now the data just sits in archives. Thousands of images, hundreds of spectra, months of photometric readings. All cataloged, all waiting for anyone curious enough to dig in. One day, maybe years from now, someone will pull up those files, run a new analysis, look with a new perspective. Maybe everything will finally make sense. The odd bits will fit, and we'll finally know what 3IATLAS was and why it survived when others didn't. Or maybe not. Maybe the mystery just stays. All we really know is that it came, it survived, it left, and we watched. Part 5, the open-ended finale. Most stories want a neat ending, a big moment where everything snaps into focus, the last act where all the questions get answered and everyone walks away satisfied. Science doesn't play by those rules. It actually thrives on uncertainty. The truth is, the universe almost never ties up its loose ends. Take 3IATLAS. Right now, late 2026 and beyond, it's heading out, putting more and more distance between itself and the sun, faster than 30 kilometers per second. That sounds wild, and it is compared to anything we've built. But in the emptiness between stars, it's barely moving. Every day, it gets dimmer. Every week, it slips away from the reach of more telescopes. Sometime in 2027 or 2028, only the most powerful observatories will be able to spot it. By the early 2030s, it'll be gone to us too faint, too far, too slow against the backdrop of stars for anyone to track. 30 kilometers per second is blazing fast on Earth. For us, it's beyond anything we've ever launched. But out there on the cosmic scale, it's a crawl. At that speed, 3IATLAS would need over 40,000 years to reach the nearest star, Proxima Centauri. Maybe it's even heading that way. We don't know, since its path only tells us where it came from, not where it'll end up. If it does end up near another star, that's tens of thousands of years in the future. On that journey, it'll be absolutely alone. No planets, no asteroids, nothing but the thin, cold dust and gas of space, so empty you could search a cubic meter and find just a few lonely atoms. There's cosmic rays, a bit of starlight from far-off suns, and the faint afterglow of the Big Bang humming everywhere. 3IATLAS isn't going to just vanish. It'll keep drifting, still following that ancient push, maybe from millions or even billions of years ago when something kicked it out of its home system. In a few million years, it could pass another star. Maybe it'll get snagged, pulled into orbit, and spend the rest of its existence circling a new sun. Or maybe it'll keep roaming, never settling down, just a wanderer slipping through the galaxy. We won't know. We can't know. That's just how it is with these interstellar objects. They show up, we scramble to observe, and then they're gone. All we get are scraps of data, and we try to piece together a story from the fragments. But here's the real question. What did we learn? First off, we learned that it's possible for interstellar comets to survive close passes by the sun, something we didn't fully expect. 3IATLAS held together better than the comets we're used to, the ones born and raised in our solar system. That actually happened. Our comet breakup models clearly don't cover everything. Maybe comets from other stars are just built tougher. Maybe they're rockier or held together with something we haven't discovered. Or maybe their endless journey through interstellar space changes them, bombarded by cosmic rays, sandblasted by dust, heated and cooled if they pass close to other stars. That could shape their structure in ways we can't really test in a lab. That changes how we think about comet formation, not just here but across the galaxy. If interstellar comets get transformed by their long trip, then every one we see is really two things: the original comet from its home system, and the altered version that finally shows up here after millions or billions of years. We only get to study the second one. Second, we found out that the line between comets and asteroids is blurrier than we thought, especially when you look at visitors from other stars. 3IATLAS acted like a comet, with gas and a coma, but it had the stability of an asteroid. It didn't fit neatly into either category. Maybe those categories only make sense because we've only studied objects from our own solar system. If someday we catalog dozens or hundreds more interstellar objects, chances are they'll cover the whole spectrum: some classic comets, some classic asteroids, and a bunch of weird hybrids that don't fit either mold. 3IATLAS might not be rare at all, out in the galaxy. Maybe it's just the first time we've actually seen a type of object that's everywhere else. This really makes you stop and think about how planets come together. Most of what we know about planet formation comes from our own solar system, with a bit of help from exoplanet data. But that extra data only goes so far. We spot exoplanets, sure, but we can't see all the little stuff, the asteroids and comets that actually make up most of a planetary system. Interstellar objects change the game. Whenever one swings through our solar system, it brings clues from another star's backyard. Take interstellar comets like 3IATLAS. If a lot of them turn out to have the same weird features, sturdy structure, odd chemical makeups, surfaces baked by radiation, that tells us a lot about what goes on in other solar systems. Maybe carbon dioxide is just more common than water out there. Maybe radiation naturally cooks up protective crusts. Or maybe elsewhere, small bodies are tougher than the crumbly comets we're used to. All this feeds back into how we think planets and their smaller cousins grow and change. Then there's the reality check. We've pushed remote observation as far as it'll go. With 3IATLAS, we got fantastic data, high-res photos, spectra, brightness measurements, precise tracking. By most standards, we did a thorough job, but big questions still hang in the air. How big is it really? What's inside? What's it made of below the surface? How did it form in the first place? To get real answers, we'd have to go there, up close, land on it, take samples. That's still out of reach for these fast-moving interstellar visitors, but it won't be forever. Someday, we'll have technology ready, spacecraft built and standing by, propulsion that can actually catch up, maybe solar sails or nuclear rockets or something wilder. When those missions launch, and they will someday, their data will blow away anything we can get from a telescope. Imagine drilling into a comet from another star, scooping up its ice, analyzing what's locked inside. We'd answer questions we haven't even thought to ask yet. For now, though, we're stuck watching from afar, squinting at distant specks of light, trying to piece together stories with just the faintest clues. That distance shapes everything we know, and what we don't. There's a bigger picture, too. 3IATLAS is only the third interstellar object we've confirmed. 3 isn't enough to start drawing hard conclusions, but it's enough to get the sense of a pattern. Oumuamua was just plain weird. That long shape, the strange acceleration, no visible outgassing. Nobody had seen anything like it. People still argue about whether it was natural or something else, and honestly, both options are wild. Then came 2I/Borisov, which was basically the opposite. It looked like a comet, acted like a comet, and the chemistry checked out totally normal. After Oumuamua, it was almost a relief. And then 3IATLAS lands somewhere in the middle. It behaves like a comet, but it survived its close pass to the sun and has some structural quirks. If you line these up on a spectrum from classic comet to total outlier, they're all over the place. Not clustered. That hints at one thing: interstellar objects are a mixed bunch. Really mixed. Lately, some researchers have started tossing around the idea of an interstellar zoo. Basically, they're saying the galaxy isn't just filled with the usual suspects, comets and asteroids like the ones we know, but all sorts of weird objects shaped by totally different environments and histories. Picture icy bodies from red dwarf systems, where carbon monoxide is more common than water, or rocky chunks from places with oddball metal content. Imagine hybrids born out of wild collisions in crowded star clusters. Some of these things have spent billions of years drifting through interstellar space, getting battered by radiation and impacts until they hardly resemble whatever they started as. If that's real, then every interstellar visitor is a chance to get a taste of the galaxy's diversity. Each one teaches us something new about how planets and smaller bodies form and change in places we'll never see up close. Each one blows open our sense of what's possible. Just look at 3IATLAS. It showed us comets can survive in ways we didn't expect, and that not everything out there is as fragile as we thought. It forced us to stop assuming our little corner of the universe is the rule. Those are big lessons. They don't solve every mystery, but they sharpen our questions for next time. And there will be a next time. Survey programs keep getting better. The Vera C. Rubin Observatory in Chile, for example, started full operations in the mid-2020s. Every few nights, it scans the whole visible sky, looking for anything that moves or changes: supernovae, asteroids, you name it. Interstellar objects, perfect targets. By nature, they're always passing through. Once these surveys hit their stride, odds are good we spot 1 or 2 interstellar objects each year. Some will slip by faint and fast, too late for us to learn much. But some will catch early, while they're still inbound, giving us months, maybe even years, to watch before they hit their closest approach and fade into the background. When that happens, when we spot the next Oumuamua or 3IATLAS early enough, the scramble begins. Think global teams coordinating, space telescopes and ground-based observatories working together, maybe even rapid-fire missions to chase one down with a spacecraft before it vanishes. The technology is there in theory. The hard part is building the infrastructure and having the funding ready so we can actually move fast enough when the opportunity appears. Whatever data we get from these future travelers will get stacked up against what we learned from 3IATLAS. Maybe patterns will pop out, or maybe not. Maybe every interstellar object is its own beast, defying neat categories. If so, that'll frustrate the people trying to build grand theories, but for explorers, that's the dream. There's something philosophical here too. Interstellar objects are messengers, but they don't talk. We have to piece together their stories from the faintest clues. A photon's color, the sharpness of a spectral line, a slight drift in position. We build whole histories from these scraps, where it came from, what it's made of, how it ended up here. Those stories are always a bit shaky. They're our best guesses, consistent with, suggests, maybe indicates. Certainty is rare. Doubt is the rule. Still, we keep at it. The alternative is to stop asking questions, to shrug and say, guess we'll never know. Science just doesn't work that way. The questions don't go away. Why did 3IATLAS survive perihelion when most comets do? We've got ideas. Maybe it's rock-rich, maybe it has a crust toughened by radiation, maybe its structure is just weird, or it's a loose pile of rubble holding together differently. Could be all of the above. The truth is, we don't know, not for sure, not yet. Maybe we never will. Maybe 3IATLAS keeps its secrets forever. Or maybe, years from now, someone will dig into the 2025-2026 data with new tools, and suddenly everything will click. The puzzle pieces will finally fit. The oddities will make sense. This isn't the first time astronomy's thrown us a curveball. We've seen it before. Data that made no sense at first suddenly clicks when someone finally nails the right model. Pulsars were just strange radio blips until we figured out they were neutron stars spinning away out there. Gamma-ray bursts had everyone scratching their heads. Then we traced them back to supernovae and neutron star collisions. And when we realized the universe was expanding faster and faster. Nobody saw that coming until dark energy showed up in the conversation. So, maybe 3IATLAS is another one of those mysteries. Just waiting for us to find the right way to look at it, or maybe not. Maybe it'll stay a question mark just hanging there, a reminder that the universe doesn't run on our schedule or owe us clear answers. Either way, the object itself couldn't care less. It made it through perihelion because physics let it. It didn't survive to teach us anything or to prove a point. It just existed, and we happened to be watching, trying to make sense of it. There's a kind of humility in realizing that. We're not the main characters here. 3IATLAS isn't here for us. It's a traveler on a path that started long before we ever looked up and will keep going long after we're gone. We got a short chance to see it, and we made the most of it with what we had. Now it's leaving. The door's closing. We're done collecting fresh data, but the work isn't over. Scientists will keep digging through everything we gathered. They'll write papers, give talks, build models, chase down every weird little detail in the data. For years, probably, but the object itself, gone, back into the dark, cold space between the stars. Someday, maybe soon, maybe in years, another interstellar visitor will pop up in our sky. Just a moving point of light, another riddle to solve. Will it be anything like 3IATLAS? Will it survive the sun's heat, or will it break apart? Will it surprise us in a way we haven't even thought of yet? We just don't know. We never do, not until it happens. That's the thing about these visitors from other stars. They don't announce themselves. They show up, they leave, and they never explain. They remind us the galaxy is enormous, strange, and full of things we haven't even dreamed of. 3IATLAS made it through perihelion in one piece. Most comets don't. That single fact, surviving when it shouldn't have, echoes in the silence where we still don't quite know why. The observing campaigns are over. The telescopes have moved on. But tucked away in the archives, the data waits. Thousands of images, hundreds of spectra, months of measurements. All the scraps we managed to gather in those fleeting moments when this interstellar traveler passed close enough for us to see it. Someone will look at that data again. Maybe they'll spot something we missed, or maybe they'll have tools we haven't invented yet. Maybe they'll ask a question no one's thought to ask. Or maybe the mystery sticks around. Maybe 3IATLAS keeps its secrets. Maybe all we get is this: it came, it survived, it left, and we watched. That's really all we ever have. Fleeting glimmers of light in the dark, stories we spin about where they came from and what they mean. The universe doesn't offer confirmation or closure, it just keeps moving. 3IATLAS is out there now, past Jupiter, past Saturn, heading for the edge of the solar system and beyond. Too faint to see, too far to follow, but it's still out there, still whole. still carrying whatever secret made it survive when others would have broken apart. And maybe that's enough. Maybe the lesson isn't about explaining everything. Maybe it's just accepting that some things last longer than our understanding. The object survived. The mystery's still with us. And somewhere in between, that's where you find this whole human effort to understand the universe. Unfinished, always reaching, never quite giving up. 3IATLAS made it through Perihelion in one piece. The data is clear on that. But why, how? No one's pinned that down yet. And honestly, maybe that's right where the question belongs. It's not because we've come up short. It's more that the search itself is the point. When we keep asking, it means we're curious. It shows some humility, admitting we don't have all the answers. It proves we're stubborn enough to keep searching, even when the universe refuses to make things easy for us. This object barreled through solar fire and didn't break apart. The reason, still out of reach. Maybe we'll get there. Maybe we won't. We're going to keep asking anyway. That's what we do. We stare up at the sky, gather every photon we can, build models, throw hypotheses at the wall, and live with the fact that some things just won't add up right away. We wait for the next visitor, the next puzzle, the next chance to push a little further. And there's something deep in that waiting, that watching, that relentless curiosity. It's an admission. The universe is bigger than us. Knowledge comes hard and never feels finished. Mystery isn't a failure, it's a door left open. 3IATLAS has slipped away, heading back into the dark. But the questions it left behind aren't going anywhere. They'll shape what comes next. New observations, better models, the next interstellar messenger. This isn't the end, just a chapter. One object in what'll eventually be a long list. A catalog stuffed with dozens, then hundreds, maybe thousands of interstellar travelers. Each one will nudge our understanding, each one peeling back another layer on this galaxy we call home. We're at the start of something big, the first humans to regularly spot and study visitors from other stars, the pioneers of interstellar astronomy. And like all pioneers, we're stumbling through uncharted places with patchy maps and tools we're still figuring out. 3IATLAS caught us off guard. Turns out, comets from other stars don't always act like the ones we grew up with. Some survive what we thought would break them. Our predictions missed the mark. Survival is possible, even when we didn't think it was. And quietly, 3IATLAS reminded us how much we still don't know. Maybe that's the real takeaway, not the details of this object, but the lesson it embodies. The universe is always a step ahead, always more complicated, more varied, more surprising than we expect. That's not a problem. That's the reason we keep going. 3IATLAS survived. We paid attention. And the story not over. Now it's outbound, late 2026 and beyond, racing away from the sun at over 30 kilometers per second. Every day it gets dimmer. Soon, only the best telescopes can pick it out. By 2027 or 2028, it'll be too faint for anything but the biggest observatories. By the early 2030s, it'll disappear completely from our view, too far, too faint, too slow to spot against the backdrop of stars. But it won't stop existing. It'll keep drifting through space, following whatever path it got kicked onto millions or billions of years ago when it left its home system. Maybe millions of years from now, it'll swing past another star. Maybe it gets captured, starts a new orbit, and kicks off another story, one that began long before humans ever looked up. Or maybe it just keeps wandering, a ghost in the dark, never getting close to anything warm enough to wake it up again. Maybe it never grows another coma, never flashes its presence to another civilization. We won't know. We can't. That's how it goes with interstellar objects. They appear, they pass by, and then they're gone. We're left with scraps of data, trying to piece together stories we'll never fully grasp. So what did we actually learn? First, we saw that interstellar comets can survive perihelion under conditions that don't quite make sense to us. 3IATLAS held together in a way our homegrown comets usually don't. It happened. That means our breakup models, built on what we've seen here in the solar system, don't tell the whole story. Maybe comets from other stars are tougher. Maybe they're packed with more rock. Maybe they're held together by something we haven't figured out yet. Or maybe their long trip through interstellar space has changed them. Cosmic rays, dust erosion, wild temperature swings if they've passed near other stars. All those things could reshape a comet over millions of years in ways we just can't simulate here on Earth. Second, we realized the line between comets and asteroids isn't as clear as we thought, especially with interstellar objects. Take 3IATLAS. It showed classic comet behavior, outgassing, even had a coma. But it was stable like an asteroid. It didn't fit neatly into either box, which kind of exposes how our categories might just reflect the fact that we've only studied objects from our own solar system. If we start logging dozens or even hundreds of these interstellar visitors, I bet we'll see them all over the map. Some will look like pure comets, some like pure asteroids, but probably most will land somewhere in between, a weird mix that doesn't match our old definitions. 3IATLAS might not be unusual at all when you zoom out to the whole galaxy. Maybe it's just the first time we've run into a type that's actually common elsewhere. Third, we bumped into the limits of what we can learn from afar. We got solid data on 3IATLAS, sharp images, spectroscopy, photometry, astrometry, the works. By astronomy standards, we really got to know this thing. And yet we're still left guessing about basics. Its exact size, what it's made of below the surface, how it formed. To really answer those, we'd have to send a spacecraft, get up close, maybe even grab a sample. Right now, that's just not possible with these fast-moving interstellar objects, but that won't always be true. Sooner or later, someone will figure out how to catch one. When that day comes, the data will completely change the game, in ways remote observations just can't. For now, though, we're left squinting at faint dots in the sky, trying to piece together stories from a distance. Zooming out a bit, 3IATLAS is only the third interstellar object we've caught for sure. 3 isn't enough for big statistical claims, but it's enough to spot a few patterns. Oumuamua, totally weird, maybe a one-off. 2I/Borisov, about as normal as you could hope for, which was almost a relief. 3IATLAS sits in the middle, active like a comet but oddly tough and different in how it handled its closest approach to the sun. If you line these up on a scale from textbook comet to total outlier, they'd be all over the place. That hints that interstellar objects aren't just a single type, they're all sorts. Some folks have started calling this the interstellar zoo. It's the idea that the galaxy's full of objects we've never seen before, shaped by all kinds of environments and histories. Maybe there are icy bodies from red dwarf systems where carbon monoxide trumps water, or rocky ones from places heavy with metals, or hybrids born from wild collisions in dense star clusters. If that's true, every new interstellar visitor lets us sample the galaxy's diversity. Each one teaches us something new about how planets and smaller bodies form and change in places we'll never go. They widen our sense of what's possible. 3IATLAS taught us comets can survive. It showed us that structural integrity isn't always fragile. And it reminded us not to jump to conclusions about the rest of the galaxy based on our own local sample. Big lessons. They don't give us every answer, but they help us ask better questions next time. And there will be a next time. Survey tools keep getting sharper. The Vera C. Rubin Observatory in Chile started full operations in the mid-2020s, scanning the entire visible sky every few nights. It's designed to spot anything that moves or changes, supernovae, asteroids, you name it. Interstellar objects are perfect for this. They're here, then gone. People figure we'll spot 1 or 2 new interstellar objects each year once these surveys hit their stride. Some will be too faint or we'll catch them too late to learn much. But sometimes we'll spot one early while it's still on its way in. That gives us months or maybe even years to watch. When that happens, when we catch the next Oumuamua or 3IATLAS early, the observing campaigns will go into overdrive. Teams all over the world, ground telescopes, space telescopes, maybe even a quick spacecraft mission if we're fast enough. The new data will get stacked up against what we know from 3IATLAS. Maybe patterns will pop out, or maybe every object will be its own thing, always surprising, always defying our categories. Frustrating for people who like neat theories, but honestly, that's what makes it exciting for explorers. There's something quietly philosophical about all this. Interstellar objects drift into our solar system like messengers, but they don't actually say a word. They don't hand us their stories. We have to piece them together from a handful of distant measurements. A photon's color, a spectral line's brightness, a tiny shift in position. From scraps like these, we try to build a picture. Where did this thing come from? What's it made of? How did it land here of all places? But these stories, they're always unfinished, always a little shaky. At best, we say things like the evidence fits, or this suggests, or maybe it means. Certainty, that's rare. Doubt is the default state. Still, we keep at it, because the only other option is to stop asking questions, to shrug and admit that some things just can't be known. Science doesn't do that, it can't. The questions hang around even when the answers don't show up. Take 3IATLAS. It survived perihelion when most comets break apart. Why? We've got guesses. Maybe it's heavy on rock, maybe it's got a tough outer shell, maybe its insides are weirdly structured, or maybe it's just a loose pile of rubble that held together anyway. Could be any of those. Could be all of them. We don't know for sure. Not yet. Maybe we'll never know. Maybe 3IATLAS takes its secrets with it. Or maybe, years down the line, someone will dust off the observation data from 2025 and 2026, armed with new theories or sharper software, and suddenly it'll all click. The puzzle pieces will finally fit. The weird stuff will make sense. That's happened before in astronomy. Data that once baffled everyone becomes obvious once someone comes up with the right model. Pulsars were just mysterious radio blips until we figured out neutron stars. Gamma ray bursts were a huge mystery until we tied them to supernovae and colliding neutron stars. The universe's accelerating expansion was shocking until dark energy showed up in the textbooks. 3IATLAS could turn out to be just like that, a puzzle waiting for the right key. Or maybe not. Maybe it'll stay a riddle, a quiet reminder that the universe isn't in any rush to explain itself to us. And honestly, the object doesn't care either way. It survived perihelion because physics let it. Not to teach us anything, not to prove a point. It just did what it did while we happened to be watching, trying to make sense of it all. That's humbling, isn't it? We're not the main characters here. 3IATLAS isn't on a mission for our benefit. It's just passing through on a journey that started long before humans ever looked up and will keep going long after we're gone. We caught a glimpse. We did what we could with what we had. Now it's leaving. The window's closing. We're done collecting data, but the analysis will go on for years. Researchers will keep digging through the archives looking for new insights. Papers will come out. Conference talks will keep the story alive. Grad students will build models, run simulations, see what fits and what doesn't. But the object, gone. Back to the cold darkness between the stars. And someday, could be soon, could be ages from now, another interstellar visitor will show up in our telescopes. Another faint point of light, another mystery to chase. Will it be like 3IATLAS? Will it survive the sun's close pass? Will it shatter? Will it show us something we've never seen before? We don't know. We never know until it happens. That's the deal with these visitors from other stars. They arrive without warning. They leave without saying goodbye. They remind us just how strange and vast the galaxy really is, how much is still out there, beyond what we've even thought to imagine. 3IATLAS made it through perihelion. Most comets don't. That single fact, survival when we didn't expect it, just hangs there, echoing in the silence of our not quite understanding. The observation campaigns are over. Telescopes have moved on. But the data's still there, hidden in the archives. Thousands of images, spectra, measurements, every fragment we grabbed during that short window when an interstellar traveler wandered close enough for us to see. Someone will look at that data again someday. Maybe they'll spot something we missed. Maybe they'll have tools we can't even imagine right now. Maybe they'll ask a question nobody's asked before, or maybe the mystery sticks around. Maybe 3IATLAS keeps its secrets. Maybe all we get is to say, it came, it survived, it left, and we watched. That's really all we ever have, little fragments of light in the darkness. Stories we tell ourselves, trying to figure out where those fragments came from, what they mean. The universe doesn't confirm or deny, it just keeps moving. 3IATLAS is out there now, past Jupiter, past Saturn, drifting toward the far edge of the solar system, and after that, who knows? You can't see it, No one can track it anymore. But it's still moving, still in one piece, still holding onto whatever secret made it tough enough to survive when so many others just fell apart. Maybe that's all we need to know. Maybe the point isn't about figuring out every last detail. Maybe it's about noticing that some things last, even when we can't quite wrap our heads around how or why. The object made it. The mystery's still alive. Somewhere between those two facts, you find the heart of what it means to be human, chasing answers, never quite getting all the way there but refusing to stop trying. The data tells us 3IATLAS survived its closest brush with the sun. How it managed that and why is still a mystery. And honestly, maybe that's exactly how it should be.